So the reason why I ask people to fill this out because no one's really going to the tutoring center. So like tutors they can't be evaluated because no one's going to get help. So we're just interested, like we may need to change our approach. Oh, you didn't get one? Here you go. Yeah. Let's see here. All right, let's see. I don't think we have embedded tutoring. Yeah, so I don't think we have embedded tutor. The only thing we have additional is SI. Yeah. All right, once. All right, guys, if you have that done, please pass it to me or turn it to me. Thank you. Any other ones? All right. Thank you. All right, so let's just continue where we left off. Just a few reminders. Chapter 11, that's the alkyl halides chapter, due this Thursday. And then please study alcohols and ethers. That's going to be tentatively due next Thursday. Okay. So the quiz on Thursday will feature the stuff we went over in lab, NMR integration, NMR coupling patterns. So do those practice problems in the handout and check your answers with the key. And then we're also going to test a little bit about alcohols, nomenclature, and then some reactions. Oxidation to carbonyl compounds, reduction of carbonyl compounds to alcohols, and then how do we form alcohols, different alcohols, by using organometallic reagents, the Grignard reagents and the organolithium ones. Okay? So if you do the homework, there are a bunch of questions on that. So use that to review and use the examples we went over in class. All right. Are there any general questions? All right. So this week in lab, we'll go over how to tackle spectroscopy problems. So basically, you're given an IR, an NMR, a formula, and you have to tell me what structure, how the structure is built, like what exactly the structure is, the right bonds, the right atoms, and there's a few techniques we'll go over to review that. Okay, but I probably won't quiz spectroscopy in total for about another 2 weeks. Okay, so just be practicing that in addition to the other stuff we go over. All right, and then next week in lab, not this week, we'll do another lab experiment. So that's going to be according to the lab schedule. Okay, so the next lab is next week. All right, so there's things you could do. There's a pre-lab worksheet. I'll go over that in lab. There's a pre-lab worksheet that you should fill out, just put in your notebook, and then come prepared to do the experiment. Okay, I'll check that before class next week. Yes?
Is this quiz also going to be tested in lab?
Yeah, so this quiz will also be given during lab. Mm-hmm. Okay. And then, okay, what else? So there also needs to be another change to the schedule. So I'm actually going to switch one of the labs on the lab schedule. Okay, so we're not going to do probably the determination of an unknown. We're going to save that for 18B. And we're going to push up the CAN4 lab to the week before the Thanksgiving break. Okay? And then when we get from Thanksgiving, basically we only have one more lecture and then it's finals. So there's no class on the 4th. All right? So don't show up on the 4th. I was going to show up, but now I'm not. Okay? So, but I'll have office hours still, so if you need help, you can ask me questions for the final exam, which I think is the Tuesday of the second week of December. But just check with the syllabus because I updated it. Okay? For the final. All right. Any questions before we start? Any questions? No? Okay. So last time we kind of stopped at carbocations, so we saw how rearrangements can occur. Okay, so just keep in mind, what I expect though is stuff on the homework. The type of rearrangements that you see on the homework, that's the level I will expect. You can expect. Okay. All right. But any questions on rearrangements from last time? So organic here is a little more complicated than it's made out to be. You always see exceptions when you do these experiments. Okay? All right. So the last thing we'll talk about alcohols, I think, here is how to make them into good reagents for reactions. Okay? So this next topic here is dehydration. Of alcohols. All right. So these are reactions with strong acids. So reactions with strong oxyacids. Okay. And what happens here, you get two pathways E1 and E2. All right. So there's three classes here. Dehydration. Let's go with the first one. Dehydration of primary alcohols. So we have dehydration of primary alcohols. Okay, so this goes through an E2 reaction. All right, so say we have propanol. Okay, we subject it to sulfuric acid, H2SO4, and 180 degrees. Okay, so for primary alcohols, they're the toughest to react because OH is not a very good leaving group, so you have to protonate it first, and then to get it to leave, you need a really strong nucleophile, and that's usually pretty hard to do. Okay, so we get propene here, so 3-carbon alkene plus water. All right, so those are our products. Let's go over now how exactly this works. Okay, so you may have to draw this mechanism if asked. Okay, so in the homework you'll have problems where you have to kind of be familiar with the mechanism to know how to proceed. All right, well, we know alcohols are basic. They have an oxygen atom with lone pairs, so they can pick up a acidic hydrogen from a strong acid. So let's do SO3. So this is just sulfuric acid with its hydrogen explicitly drawn to show that the hydrogen here can be accepted. So we get bisulfate as our conjugate base, SO4 minus, and then we get our intermediate oxonium ion, which is now a good leaving group. So now it can leave much easier than a hydroxide would because, oops, sorry, let me just erase that. Only one lone pair now, so positive charge. Okay? All right. Well, since it's E2 and it's a high temperature, what is I have another molecule here of alcohol. So what is this going to attack? Is this going to grab an H, or is this going to grab or bond to a carbon? Based on the products that we just drawn above. What do you guys think? Yeah, hydrogen zinc eliminating a hydrogen. So we're going to attack this hydrogen. Okay, and that's because if we remember entropy, so higher temperatures, it favors entropy. So you're going to have the process that produces the alkene, because producing the alkene actually gives you more products. So that's why we get this going here, and then the water formed here. Okay, and what we get here is propene plus propanol again, the protonated propanol here. So let me just zoom over there. Okay, and then if we draw another H over here, okay, the water here can go here and pick up another hydrogen. Okay, and what you get here, the total products you get here now are 2 propene molecules. Okay, and you get the H3O acid here is regenerated. All right, because remember here, this right here is a catalyst, acid catalyst. All right, it has to be regenerated. So here, acid is regenerated. It is recovered And then this acid can just go through the cycle again. So that's how the acid's recovered. All right, so high temperatures, elimination. Low temperatures, substitution. That's usually how we explain that one. Okay, are there any questions on this process? Captain.
So since the acids recovered in the cycle can repeat, are there like termination steps?
No, you don't have to worry about that. There's no radicals, so don't worry about any like termination steps. Yeah. So this acid just goes back here to this step. All right, so it just recycles until every alcohol is converted into alkene, and then it's over. All right, so here I can say re-enters the reaction. All right. Oops, if I could spell. All right, so that's primary. What do you guys think the mechanism will be for secondary and tertiary alcohols? Do you think it's going to be like SN2 like this? Or sorry, not E2 like? Or is it different? Yeah, E1. So you're going to get the formation of what intermediate? Yeah, exactly. Carbocation. All right, dehydration of secondary / tertiary alcohols. Okay, so here the mechanism will slightly change, E1 reaction. Okay, so let's show an example of the carbocation forming in solution, okay? So here we have our cyclo, so our 1-methyl, 1-cyclohexanol. So you notice here the temperature is decreased by a lot, by 80 degrees. And that's because the alcohol, it's easier for an alcohol to leave and form a carbocation because it's stable, okay? For primary, we can't do that because primary carbocation, like we saw, is not very stable. So that's why this one has reduced temperatures, but still does elimination, okay? So still you're going to get the most stable alkene in this situation. So always draw the most stable alkene when you have lots of heat. So that's the tetra-substituted. It's tri-substituted alkene right here. All right, you have 3 carbon groups here. 1, 2, 3. So tri-substituted alkene. All right. And it doesn't matter if this double bond is on the right side or the left side of the ring. That's the same product. So you don't have to worry about choosing a side, okay? But you shouldn't choose the, you shouldn't draw the alkene at this position. So don't draw the alkene over here. And that's because that will be only di-substituted, not as stable as the tri-substituted. All right. So let's go over the mechanism here. So very similar. What's the first step of the mechanism if we compare it to the previous one we just drew? Yeah, what's up?
If this is like a regular kind of reaction, always will be a poor leaving group, right? So like technically no reaction will take place.
Oh yeah, but in this case we have acid. So yeah, if there's no acid there, say I try to substitute sodium chloride or sodium bromide, you would say no reaction. But the thing we're doing here is we're turning this group into a good leaving group by protonating it first, and that's why it leaves pretty well. All right, it's not the best leaving group, but it makes it so that we can actually do a reaction. Good question. All right, so what's the first step in this reaction here? Yeah, so we're going to deprotonate the acid, and the acid is going to donate one of those hydrogens to the more basic alcohol, right? So let's just redraw what we did before, SO3, OH, Okay. Oh, sorry, I drew that wrong. My bad. So this should be an O first. So put an O there, then SO3H. All right. So we still get bisulfate as our counter ion, our conjugate base. And then here we get the protonated alcohol. So we have an oxonium ion here. Okay. So you might be wondering, why don't we just eliminate 2 at the same time as this group is leaving? But the reason is, since the carbocation is so stable, this is like magnitudes faster, so this just leaves first, okay? So we're going to show this group leaving first, okay? And then we get a tertiary carbocation. All right, but the tertiary carbocation does not stay there. So what happens here is that there's a few ways you can eliminate, okay? So you have 2 options here, all right? But if you let this reaction kind of cook and heat up a bit, it will eventually equilibrate to the more stable alkene. So that's the tri-substituted one. So water, you could use water, or you could use another molecule of the alcohol, but let's just use water because that's a lot simpler. Okay, you just need to write a plausible mechanism, and this H now will form a double bond there, and now the carbocation has been neutralized. So there's no more reactive intermediates here. So the final product is generation of this alkene plus H3O plus, and the H3O plus just gets cycled back to do the reaction again. Okay, so that acidic hydrogen gets recycled. And let me just make this note here. The major alkene products, so major alkene formed is the more substituted alkene. So let's just underline that. More substituted. What does more substituted mean? It means your alkene has more bonds to carbon atoms around it. Okay? So less hydrogen atoms on the alkene itself. All right, so that's dehydration of alcohol. So this process happens a lot in organic chemistry, in human body. So there's dehydration, rehydration reactions. That's how your fats can kind of get converted into alcohols, and that's how energy is processed in your body through oxidation reactions. Okay, are any questions on those examples? No? Okay. So now let's do a few more examples here for dehydration. So we talked about primary, secondary alcohols. Now let's talk about rearrangements. All right. So we're going to do E1 reaction and carbocation rearrangement. All right. So we talked about rearrangements before. So this is going to happen when we have a carbocation, okay? So let's say we have this alcohol, and you see here it's very close to this substituted position right here. So you can kind of imagine a carbocation rearrangement can take place. So I might not tell you this, that rearrangement will occur. You have to kind of detect that intuitively based on the structure, okay? So say I have H2SO4. And I just heat this a bit to 140 degrees Celsius. All right, and we'll notice here, this is the major product as confirmed by NMR and IR. All right, so a few things to note here is that look at here. I had 3 methyl groups right here. I now have 1 that has shifted. Okay, so that's your key here, your hint that a migration has taken place or rearrangement. So now let's talk about the mechanism. All right. So in terms of the mechanism, pretty straightforward. It's pretty clear what happened. Just think about it. The first step we do, right? Protonate, and then what happens to the alcohol? What forms is it? What intermediate forms? Yeah, more carbocations. Okay. So let's just redraw our alcohol here. Show the lone pairs, and we're going to show the acid being donated. So let's redraw those oxygen atoms here. All right. So we got HSO4. Okay. So pretty similar to what we've been drawing before. So here now, water has been formed and it's itching to leave here. Okay. So we're going to show that the water is going to leave, okay? And then we're going to get a water molecule coming off here. And then we're going to draw the carbocation. All right. Well, it looks like a methyl group shifted to where that carbocation is. So what's the rearrangement going to look like? What group is going to migrate to the carbocation? What kind of group? A hydrogen atom or a methyl group here? Yeah, so let's take one of these methyl groups. I'm going to circle it, and it's going to shift over here. So basically, the carbocation, the charge, and the methyl group are going to swap places. So what you get now is a carbon with no methyl group, missing the methyl group, so it has a positive charge. And now this carbon has gained a methyl group, and now it has an octet here, okay? But there's still a hydrogen sticking out. So that hydrogen didn't move, right? Still there. Okay, so there's only one last step we do. So what does water do in this case? Yes, deprotonates the hydrogen to form the target alkene here. Okay? And that's the only product you get. And that's because this is the most stable alkene, a tetrasubstituted alkene. So that has a high probability of being formed. Okay, so you get that plus the acid is regenerated, and that can be then recycled to repeat the whole process over again. All right, so that's an example where migration occurs. You can either have a alkyl shift, any carbon group shifting, or a hydrogen. So in this case, it was an alpha group. All right, any questions on that example? We're going to do a few practice problems here, okay? Just so we can practice this. All right. So let's write these two problems down, and you're going to help me predict the products. Okay. So here's the exercise that we'll do right now. So I want you to write the major organic product of the following reactions. Of the following but I also want you to show me the mechanism. So show me, or show the mechanism. You don't have to show it. I don't have to include myself there. Show the mechanism. Okay, so the arrows that, the examples we've been doing so far, I wrote the reaction out, predicted the products, and then I wrote the mechanism. Okay, so here's your reaction. All right, well, you take 5 minutes, predict what products can form, and show me the mechanism, okay? So I'll tell you right now, only do rearrangements if there's a nearby carbon that can have a better carbocation. So if the carbocation and the nearby tertiary position is too far away, don't do a rearrangement, okay? So here, I'll just tell you here, there's 2 similar products, all right? So here you want to see how many products you can get. You have 2 similar alkenes, similarly substituted alkenes, okay? All right, let's see if we can determine what those are. All right, take about 5 to 6 minutes. All right, I'll be right back. Hey, what's up, Kevin?
I'm curious, I don't know if that's what I tried to learn to do semester. All are the one that are the same, like,
Yeah.
and they all have to go hydrogen. And they all options are different, and it helps in the hydrogen.
Oh, okay. So you're saying
Yeah.
help that one off?
Yeah.
No. So it'll just give you like, like there's no way to kind of deprotonate that, just because it'll, yeah, more positive and then lone pair, so that's what we'll do. And then if you try to form a double bond, you need hydrogen to make that possible. But yeah, there's both the ones and those two ones. All right, what we get? How many alkenes did we draw? Two different alkenes? Yes? All right. So what's one of the products here? Where's the alkene? Where's the double bond at? All right. Is it, you mean right here?
Yes.
All right. That's one. What's the other one? Yeah. All right. So we could draw it there, but we could also draw it right here. Okay. So these are not exactly the same compound. They may look similar, but they'll have different boiling points. But they'll be very similar in terms of their physical properties. But you can actually differentiate these two by NMR. Okay, so these are two different products. All right. So the other question here was to focus on how did each of these form. So you should have started with protonation. So let's protonate this alcohol. All right. So I'm going to write the alcohol here. All right, and then we have, let's write HSO4 right over here. Okay, so, yeah, Kyrie had a question?
If we had this type of question on the exam, would you also want us to show the hydrosulfuric?
No, you could leave that out. It's fine. Yeah. All right. So this is a secondary alcohol, right? So it's going to proceed through which mechanism? E2 or E1? All right, I think I heard one. E1, right? Because it's a secondary carbon. So let's have water leave. Okay. Now we're going to have a carbocation. And a carbocation can be, we call it quenched, all right? Or it can be reacted away from two positions. So both of these hydrogens have equal probability of being attacked by water. So there's really no clear winner here. So you want to draw one water molecule, removing this hydrogen to give you this product. So I'll draw this product in black right here. So you have the double bond, one bond removed from the methyl group, plus the acid regenerated. But you can also have another water molecule attacking the other. So these are two different pathways, all right? So this leads to two different products. So my red arrows are going to be illustrated in this arrow right here below it, okay? So we get two different products here. And depending on which product you want, this can get complicated in terms of product mixtures. So purification here becomes really important. All right, so you have two alkene products. Now, on say exam or something, you might be asked to draw the major products, and then a follow-up question might be, all right, well, say you have two different alkenes being formed. Suggest a mechanism or suggest a intermediate that can give you a reason why two products form, and you would show something like that. Okay, so got to think a little critical here based on what you know about the reactivity of carbocations. Okay, are there any questions about this? So we revisit carbocations, how they shift, and then how the products are formed based on that intermediate after they get nucleophilically eliminated or attacked. Okay. Any questions about this step before we move on? All right. Well, let's take a little break there. We'll be back at 2. Okay. Then we'll talk about the rest, how the better ways to make alcohols without rearrangements. Okay.
When you form a carbocation, you have to look, okay, is this the most stable carbocation? It's secondary, but tertiary is not stable. They can only move to a carbon next to it. Like, you have to look to the left and right of it. Okay, is there a tertiary carbocation that I can move the charge to it and be more stable? Since there isn't, and they're all three of them are secondary,
Oh, because we can get to a more
then
stable
either
carbon.
you then will just keep the height, you keep the line of the charge where it is. And
So this is secondary, only 2 carbon groups, so you got 3 carbon groups right here, and this one
Either one.
stabilized.
And you want the double bond to be
Even better.
towards a carbocation. Possibly.
So that's why I took it. Yeah. Just for that.
And I have a question.
Charge on carbon.
Yeah.
Okay, that's fine.
Carbocation.
Oh, there you go.
Not healthy snacks, good snacks.
Hey, you're eating something. You need to burn the energy.
So there's 3 different houses you can form. Oh wait, draw the major elimination. Oh, you're missing some.
Situation like this. One of them now wants to move that whole.
Well, keep it wet. So that one, which one's that one dash? No, the one you have 4 dash. Put dash. Now,
She's gonna help. She's gonna help, but she's gonna stay around to help find.
remember,
I would have helped you did.
yeah, the top face and the bottom face. So you should draw.
And so we agreed.
3 switches.
It's like so good.
As a part of the, she posted a
That
listing
one's
for
okay,
it.
but for this one?
Yeah.
So why? Because I
So I would just draw the same thing. Remember, alcohol gets out of the top face
Most
and the bottom
expensive
face.
room.
So now the top, that's from the top face, right? That's
Yeah.
the switch. So I would just draw the
Another
same
student
thing.
too, that
Or like,
Switch to
like I was
bottom
doing
between
hours
alcohol
or
or
like grad student, like we don't want another grad.
Yeah.
Yeah, it'll be the opposite.
Oh, so it'll be dashed?
Yes.
So she posted and I was like, okay, like what if it takes so long? And like, she was like, well, tough it out. And I was like, but then I think it works because last night,
Let me test
my
you that.
third housemate broke with her boyfriend.
Thank you.
Yeah.
Oh, no, one more.
Oh no, you were dating for a while too.
Almost 2 years.
This one. And then this one.
And she like came home, she was crying. I was like, what happened? She's like, we broke up. I was like, He was just here this weekend.
Probably for a while we did.
Oh, so what kind of reaction is this?
Because like, we were having a normal, like, I guess, good night
Yeah, so you're gonna
conversation.
draw you're
The
gonna draw
conversation
your
that
image.
I had is like a very good very much.
Yeah, the CN now we got the left hand side,
And she's really angry, and she's like,
and then all these versions are on the face.
and he's not like about that.
But, and also he said it's over just as that.
She was like, doing it, but he was like, I
So where's
don't
the
wanna
scene
feel
go?
like I'm in a jailer, like holding me back from.
What's your opinion?
That was really busy.
Well, it's substitution, right? So you're gonna put the bromine now.
For you to let me go.
Yeah.
And she was like, I'm not so sure, and then he just like, he was very much like, this is the end, like, and he just like, like, boy, maybe like she doesn't want to go.
And yeah, that wasn't her.
Like, she didn't want to, that wasn't what
Oh, yeah,
she was talking about before, and he was like, well, I wouldn't feel like I'm holding back from.
You
opportunities,
make
different
maybe
type of relationships we were trying to have, and.
God, that's tough too. So she really did
Bring
bring
him
it
not
up.
directly involved, but that's what, like, he just like, he's very, from what she was explaining, he just seemed to be very much like, oh, when we break up, we get back together, and all that, and she was so.
That's what it's over your birthday.
Oh, so the last one, partners and
Great.
I'm sorry, this is so much emotion too with.
You got your people together.
Okay, well, you're gonna keep those two groups the same, right? You already inverted it, so I'll keep that.
My other housemates this morning,
And then one of them's gonna be a dasher.
do you any photo? And she was like, our house is cursed, and I'm like, well, it's not cursed.
So you
I'm
can
I'm vibing.
So you flipped it and then it's left.
it's substitute for SH2, SO2 for inverse stereochemistry, and it's substitute for leaving group, yeah.
So you don't switch the dash.
No, because I drew the mirror image synergy. So you could do two things. You could draw the same product here, but switch to stereochemistry of those bonds, or just draw the mirror image. No. What happened? Okay.
The alcohols, reaction of alcohols.
Alright, I put the
You'll get it, you'll see it, you'll understand it.
Okay.
I don't know, we'll see.
I guess we'll just draw in the major organic
I
product.
have to be well this.
You haven't moved
like, I
bromine?
don't-
No, you're alright.
I like started drawing my
Thank you.
Yeah, you're welcome.
Don't want to draw the lobster or something. For that one we just did.
No. Unless there's a formal charge, just draw the correct formal charge and you'll be fine.
You know how you said these are secondaries?
Yeah.
How come they're not primary? 'Cause it's just one.
No, it's the carbon attached to the secondary.
Oh, okay.
Yeah, the hydrogen is just like, it's just, yeah, even though we're only at one hydrogen, it's two hydrogen, so there's like two options, but it's like.
No, some people have to take it slow.
It's a hydrogen at one hydrogen and one of those carbon.
Okay.
So that's why there's two options. If we wanted to consider the stereochemistry, then there'd be four options. Because again, there's two hydrogen.
My boyfriend, I don't know, he always looks at houses. I don't know why. But he found this house in Monterey that's a mile away from me. And it's a triplex and a duplex on the same lot. And it's built in 1970, so it's like a Victorian one. And, yeah. Oh, it's a 1970. And when he looked at the foundation, it's like, it's so bad. Like, he's never heard of a Victorian house. Well, it's not considered Victorian, but
Victorian style.
yes, yes, but it's, so it doesn't have a plaque that says Victorian, but Monterey City will only allow you to remodel it to an extent. It has to remain its historic, structure. That's why it was so weird, but yeah, it's 1970, so we got someone to go and inspect it. Like, the foundation of the house, the things holding up the house are bent. Like, it's so scary looking, but he was like, we make, it's like a good, big income thing to bring in and whatever. So I was like, well, it's 14 million offer, definitely less, because they're gonna have to rebuild to the town. They put in an offer and they're like really leaning towards it, but he found a cheap contractor and do everything to fix the whole house, so. Well, yeah, he just wants that to basically bring in. Yeah, yeah. He bought a house like in 2002 in Monterey that he paid off, so that's where he said like he would move after and then with school, but I'll probably move out of state when I get into the program. But that's like way. Yeah, because I mean, I'll never apply to California schools, but we both would like to move out of state to check for a couple of years and come back to California for residency. I want Louisiana. Yeah.
Girl.
Really?
Isn't that okay? Well, that's like Jamaica, but like, I'm just people, the culture is beautiful. I love it down here. My brother
That's
school
what
down there.
we both have.
It's so hard to get like insurance for our kids. Because like depending on what you have to, especially like you have to avoid like houses that are rebuilt period for the treatment. So a lot of them go super cheap, and so like there's no like I would like a lot more risk with my brother.
Okay.
And like it's safer to sometimes like get a house further down in the city, but not to get to where like the flooding zones, the flooding area.
Yeah. That or we talk. Like those are the two that I like mentioned. I like this school. Yeah, you guys were like it's so pretty and just I'm really obsessed with like historical museums and just history and I know.
You know what I respect so much is really we also like the town I grew up in has historical society, so the more like houses like flats and like they were those that like super controlling what you can do to the house.
Like an HOA if it works.
Yeah, it's more controlling, especially the fact that like they restrict you with what you can do to the house. Yeah, it's like okay, like yeah, like you can replace the plumbing or whatever, but like certain historic parts of the house you can't do. So like my mom's parents' house was a historic house, and we sold it off to people who like your husband who bought it and wanted to do it themselves for their parents because it was so groundbreaking decision.
Yeah.
And a thing is that was a historical site where like okay, you can't really assign me to it.
Oh wow.
Without like tearing it, because like there's a main historical house and it's like they can't like they can change certain interior parts of it, but there's certain parts of the house like there's like an old chimney place.
Yeah.
Like there's like some walls are like you can like not move that walls or like you can like adjust like a room into like two rooms into a larger room, but like it's certain parts of the house have to remain the same.
That's insane. Like, why is it really restricted? That's sucks.
Like my parents, when they bought the house, they were also historic, but like, so your parents like told me to since they wanted to redo it, so they had to get it removed, to, like, redo it, like, try to get it fine.
Yeah. So if I can do like this, like all the toilets and sinks have to be changed because it has to do like the Monterey guidelines on water, like the 200 gallon or something. He was saying.
That's what I could fix my grandma's place because that is still from like.
Yeah, but that should be fine, you can still have it.
Yeah.
My mom would probably more than the money to do all that, but like I would sell it, and like, this is my dad's gift for playing games all my dad.
Yeah.
I was like,
All right, let's continue on here. So a few more reactions for alcohols, and then we'll be moving on to ethers. And I might talk about diol ethers. I might just mention it briefly about why they're important. Sulfides. All right. So now there is a way to convert alcohols into good leaving groups in one single step, and you don't have to worry about carbocations, okay? So let's talk about that. So synthesis. So first we're going to talk about transformation of primary alcohol to chloroalkane. So remember, we discussed before, you can't really do this with HCl. Chloride here is not, it's a good nucleophile, but the leaving group is not as good, so it's very sluggish. So you need some help. All right. So the way we do it here is we have our primary alcohol, so some R group, primary carbon atom. Here's the alcohol. So we use a reagent called dianyl chloride, SOCl2. All right, now this reagent is hard to get, and I think it's because it's been used to make illicit drugs. All right, so you can't really buy this stuff in bulk anymore. It's very hard to get, and is a very versatile reagent, very powerful. All right, so here you have a weak base called pyridine. We saw pyridine in PCC. All right, so pyridine is basically here to mop up or absorb any HCl generated in the reaction, okay? So the transformation here, you get rid of the OH and substitute it for a Cl, and this is synthetically more useful for us, okay? So the byproducts are great because they're gases, so they'll just evaporate out of solution. Sulfur dioxide, that'll just evaporate. And then you get the pyridine salt, which can just be washed with an aqueous water wash. And then you're done. Okay. So this will become now pyridinium, so the conjugate base, acid of pyridine. And then your Cl minus will just be associated here as a ammonium salt. So pyridinium chloride. All right, so that's good and all. So if you want to convert an alcohol to an alkyl chloride very efficiently, you want to use dinyl chloride and pyridine. But the question is now, how does this take place? So how exactly does this mechanism work? All right, so let's go over that right now. So here's the mechanism. All right. So dinyl chloride looks like this. So this sulfur may look trigonal planar, but it's not. The sulfur has a lone pair right here. So I'll just draw a bond to it. Here's the lone pair. Okay, so it's actually sp3 hybridized. It's tetrahedral. So what happens first is your alcohol is going to displace one of these chlorines and bond to the sulfur. So SN2-like reaction. When that happens, your alcohol is now converted to a better leaving group. Okay, so now it looks like this. So let's draw out the alcohol. The O bond. We have an H bond here. It's positively charged now. So we now get this intermediate right here. Okay. All right, so the pyridine now will come into its role as a base. It's going to deprotonate the hydrogen here. So whenever you have an acidic hydrogen, a good next step is to deprotonate it. So once you have that, you will now have the first byproduct, which is the pyridinium salt right here. All right, so we have the conjugate acid of the pyridine, and then we have the rest of the R group here. It's our modified alcohol here, OSOCl. We're just going to abbreviate it for now. Okay, So we're not done because the chloride is actually still floating around here. The chloride is still floating around in solution. So the next step is our chloride is going to perform an SN2 reaction on your intermediate here. So the R group is going to be, well, the R group is going to stay, but what I mean here is the carbon-oxygen bond is going to be broken. All right, so chloride, this bond, this is the partially positive carbon, not the R group, because that one's attached to the oxygen. Now, this oxygen bond is actually going to go to form a double bond and kick off this chlorine here to give off SO2 gas. So what you get here is your alkyl chloride, or CH2Cl, plus sulfur dioxide with the two double bonds there. And then you're going to get, this still has a lone pair. So let's not forget the lone pair here. Okay, so still has a lone pair, SO2 plus Cl minus. So the Cl minus will just come together with the pyridine salt and become probably pretty much just crash out solution. Okay, so that's how the substitution works there. Okay, so that's the transformation. SOC, you see here, we did not have any opportunities for a carbocation rearrangement. So that does not happen. Okay? All right, so we can also do this for secondary alcohols as well. Yeah, Captain.
So just to clarify, the chlorine ion is going towards the carbon because it's partially positive?
Yeah, so here the oxygen is partially negative, and these bonds are partially negative, right? So they're kind of pulling electrons away from this carbon. This is partially positive now. Yeah. Just like we saw before in the SN2 reaction, the carbon there is still partially positive, but now we have a better leaving group. All the electrons form a gas. So if you could lead to a gas, that's very favorable. It'll just go off. Okay? Yeah. So it's an even better leaving group than water. Okay? So we don't get any rearrangements at all. And this we can actually do this with chloride now. Where in the past, if we use HCl, I couldn't tell you that it would work 100% because it's way too slow. Okay, so this is one of those reactions we want to remember. Alcohol to the primary alkyl halide use SOCl2, so that's called dianyl chloride. Dianyl chloride. But if you just remember SOCl2, I don't know what you're talking about. If you kind of misspell it, that's fine too. As long as it's not like anything else than sulfur, we'll be okay. Okay? All right, are any questions on that reaction? Alondra.
Is that just part of the products too, the restructure? I mean,
Oh, you mean this one? This structure right here?
yeah.
Yeah, it pretty much is. It's part of the byproducts, yeah.
Oh,
Yeah.
but we don't have to.
You already wrote it there, so you don't have to write it at the, you don't have to write it again, because you already wrote it. If you wrote it in that step, that's fine. What's important is that you show that it forms. Yeah. All right, any other questions? Okay, well, there's another one, so that's for primary, right? Dianyl chloride works great for primary. All right, if you start using it for secondary though, things can just go wrong. So don't do it for secondary. So dianyl chloride is also, this reaction can also be solvent dependent based on the substrate. So just use this reaction for primary alcohols. Okay? All right, now let's talk about secondary. Tertiary, we don't usually worry about just because you can pretty much do that already with a tertiary alcohol with just regular old acid. All right, but let's talk about secondary. So transformation. of secondary to haloalkanes without rearrangement. All right, so say we have this secondary alcohol. And it's nearby a tertiary position that you can rearrange to. Okay, so that's not ideal. So there's another reagent you can use. So this is called phosphorus trihalide. So the X here can be any halogen except for fluorine. So X can be chlorine, bromine, or iodine. The one that works the best and the most common one is Br, when the X is bromine. Okay? So what happens here, here's your solvent. Don't worry too much about solvent, okay? What's more important is the reactants. So this actually preserves the reacting center. So you do an SN2 reaction on the alcohol without rearrangements happening. So that's pretty good. So if you don't want rearrangements, in most cases you don't. For example, when you're trying to make a natural product, you can't have it rearranged on you because you won't get the target that you want. Okay? So that's our goal. So let's explain how this works. So here, the mechanism is very similar to dinyl chloride. So one thing I want to try and get across is these patterns of reactivity, that they're just, if you just kind of understand how one works, you can understand the rest. All right, so like last time, this reagent here is actually tetrahedral. So the phosphorus halogen bond is very weak, so it's easy to break. So that's the bond that's going to break first. So I'm going to have my lone pair attack the phosphorus and kick off one of the halogens, okay? So now I have X minus. A free-flowing halide ion. So a pretty good nucleophile, like we learned, okay? And then what we get here is what we call a phosphate ester. So here, this carbon is still preserved. So let's just shade that wedged. And notice here, I didn't attack the carbon, so the stereochemistry did not change because my oxygen is the one attacking. So I get OH here. All right, and here's a lone pair. And now I still have my PX bond. So I could just abbreviate this now as PX2. Okay. All right, now, what do you think is going to happen here? What's the last step? What does the X do? Yep, backside attack, SN2. All right, so it's going to approach from the opposite side of the leaving group and kick off the oxygen here. And what you get here is your major product. The stereo center has been inverted, and you get substitution with the X, and then also here is still the methyl group. And now the product that comes off here is this group. All right. And then what happens here is that this reagent can react 3 more times. All right, you can react 2 more times. So I can take 2 more of the alcohols, okay, of the starting material. And react this remaining reagent here and substitute the 2 X's again And so this usually goes to completion. And if you need to quench it, you can actually just put water in here to react with this phosphorus group. So you get 2 more of these. And then your byproduct here is phosphoric acid. And phosphoric acid won't react with an alkyl halide, so you don't have to worry about any side reactions. So that's how that reagent works. Converting an alcohol, secondary alcohol, to secondary alkyl halide, and then you can do some more chemistry with that. So this prevents rearrangements and side products. So it limits the amount of products you can get, which is pretty useful. All right. Are any questions on that example? All right. There's two more transformations I want to go over. 2 more useful ones. Okay. But are any questions on using PX3 here? So PX3 could be PCl3, PBr3, or PI3. Doesn't matter which one. All right. So there's another way to make alcohols here using alkyl sulfonates. So let's see that one. Using So we can use these sulfonates to make good leaving groups, and then that can do interesting chemistry. Okay, so for example, we talked about these groups before. They're great leaving groups. So usually you have your alcohol here. You have the chloride version of the sulfonate you want. So for example, methyl sulfonate. So this is called methane sulfonyl chloride. So that's the reagent you would use. All right, and so you would use a base here to neutralize the HCl. So usually it's pyridine or triethylamine. So usually this guy, or that's 6, yeah, that's 6. Or triethylamine here. So these are just weak bases. Okay, so these are weak bases. Weak base. To deprotonate the HCl. All right, so here you would get, so notice the alcohol is still intact, SO2, CH3. So I added the group that was bonded to the chlorine. So here, this group right here is a great leaving group, one of the best. So great leaving group. All right. And what happens here is this H, and you also get an equivalent of HCl. Okay? And the HCl here, that will get mopped up by the pyridine, so you don't have to worry about it being a problem. Okay? So the other thing you would get, so this actually turns into this guy. Okay, so this HCl goes here and becomes pyridine, like we saw before with the pyridine as the base. Pyridine HCl. Like that. All right. But what's the point of making this group in the first place? Well, this is a 2-step way to convert an alcohol to an alkyl chloride. So not the best because you have actually 2 steps to remember. So this is the first step, forming the alkyl sulfonate. And then 2 is using it in our example. So let's use an example here. So here's the second step. You would take, here's my example. Let's just show an example of how it's used. All right, so say I have my alcohol here and my methyl group here, 2 stereocenters. I'm going to take my, my sulfonating agent, SO2, Cl. All right, so what I get first is an intermediate structure that looks like this. All right, so S, O, O, CH3. So notice here, this didn't affect the stereochemistry at all. All right, so it doesn't affect the stereochemistry because the carbon is not being approached. Okay, And then here you can use an appropriate nucleophile and do what kind of reaction here? Backside attack. All right, this type of question was on the second exam we just took. All right, so SN2 type reaction here. So here, iodide would come around, kick off this group, and you'll get the iodide substituting. So this is also another way to avoid carbocations. Okay, so a carbocation probably won't form if you use a strong nucleophile. Do SN2-like conditions, very concentrated sodium iodide solution, and polar aprotic solvent. Okay, this will favor SN2, so you can get this product probably almost exclusively. All right, so that's using alkyl sulfonates. So you have 3 ways to convert an alcohol into a better leaving group and do SN2 type chemistry or elimination, stuff like that. So you limit the number of products you can get. All right, but for elimination, elimination is a little more tricky because you can get multiple E2 products. So substitution is probably the best for reactions like this. Okay. Are any questions? All right. So let's go over one more reaction of alcohol. So this is a specialized reaction, and this is usually not taught in textbooks, but I want to show it to you anyway, just because it's really cool. All right. So what if you can do the reaction we just showed you in one step, but and the only transformation you get is inversion of the alcohol itself. All right, that'll be pretty cool. So let's answer this question. What if you could do an SN2 reaction in one step on an alcohol? All right, and this is not using any alkyl halides, using any halide ions, okay? So this is called the Mitsunobu reaction. All right, so I just want to introduce you to this reaction. You do not have to reproduce this mechanism, and that's because it's quite complicated. All right, so here's the general reaction. You have an alcohol, and you have a nucleophile that's protonated, okay? So say, for example, water, H2O, all right? And you're going to add 2 kind of reagents here. So one is, first, this one's called triphenylphosphine, PPH3. And this molecule here has an apt, appropriate, I don't know, kind of foreboding name here. All right, so this is, so when we have an NN double bond in the molecule, that's called an azo compound. So it's used in dyes. All right, so this is abbreviated DEAD. All right, and the full structure looks like this. An ethyl group, CH3, CH2. It has 2 esters coming off it. And the nitrogen atoms are still right there, okay? Oh, sorry, I just messed up. No, I'm good. All right, so this is called diethyl. That's where the D comes from, diethyl. Okay, diethyl, azo, A, dicarboxylate, the last D. All right, you don't need to know how to name that, but that's abbreviation is DEAD. All right, So the transformation here is you will create a new bond between R and your nucleophile, okay? So the nucleophile replaces where the oxygen or alcohol was, all right? And now let me just draw the structure of PPH3. So it's a phosphorus atom bonded to 3 phenyl groups. So 3 benzene rings. Boom, boom, boom. And then there's one coming off in the back here. That's what it looks like. So this is called triphenyl phosphine. And this is a useful ligand. I'm not sure if we remember what ligand is from Gen Chem. But basically, these can bind to metal atoms. And they form efficient catalysts in organic reactions, okay? All right, so the mechanism here consists of 4 steps. So let's go over them one by one. So number 1, so here's the mechanism. Let's talk about the mechanism. How do we get substitution like that? Okay, so let's redraw dead. So when we have a double bond here, that is subjected to attack, as we'll see in the alkenes chapter. Okay, so the lone pair on the phosphorus is going to bond to nitrogen. The bonds will break and from the double bond go back to nitrogen. And we're going to get this intermediate. All right, ETO2C. So let's draw out the nitrogens now. So now this phosphorus will gain a positive charge. Okay, this nitrogen will gain a negative charge. And then this, well, we should draw out this carbonyl, so COOET. And you'll notice here you can draw a resonance structure. So let's practice our resonance structures. To localize this negative charge right here, put this charge on the oxygen. Okay? So this structure is favored by resonance. So ET, O2, C, N, P plus PH3. All right. And this N is stabilized by resonance. So we're going to draw this structure like this. Like that. Okay, so here we have stabilization of this negative charge by resonance. Okay. So we have activated dead. Okay, so that's going to help us activate our nucleophile before we substitute. Okay, are there any questions by these steps? So the triphenyl phosphine interacts with dead. You form a negatively charged anion on nitrogen and oxygen. And now that's going to be linked to the second step here, which is the activation. So let's do number 2. Activate the nucleophile. So let's activate the nucleophile. All right, so let's redraw our structure. Yeah, I know it's kind of a pain to redraw this structure all the time. Dead. I guess that's why it's called that. It makes us, after a long time of this, it makes us want to be dead. Okay, so PH3. All right. So it's important that your nucleophile has an acidic hydrogen, or this intermediate right here will interfere with your reaction. So there's some limitations, but still a very cool process. So you can kind of see why this has been studied for so long. All right, so your nucleophile, it can be anything. Usually it's a carboxylic acid, okay? So you can form esters from this. So you're going to take this hydrogen here, and then your structure here, you're going to substitute this negative charge with a hydrogen on it. All right. So we got the phosphorus, pH 3. Now the N has grabbed that H. Okay. CO2, ET. All right. Now we have the nucleophile. It's deprotonated, so now it's a even better nucleophile to do the substitution. But we haven't even introduced the alcohol yet. All right. So now we have to talk about the alcohol. Okay. So step 3. The alcohol finally make its entrance, all right? So let's go to step 3. But are any questions why some of these steps? They're kind of very familiar. Acid-base chemistry, nucleophilic attack by phosphorus. Phosphorus is a good nucleophile relative to oxygen and nitrogen. And then we get stabilization by resonance. Okay, so 3 here, the third step. It doesn't really have a name, but that's where the alcohol comes into play. So, let's redraw our alcohol. All right. So, let's first draw the phosphorus part of the compound. And then draw the rest of the compound. All right. So, we can actually just keep abbreviating this because it's going to be a pain to just draw everything out all the time. All right. Well, the alcohol is weakly nucleophilic. This phosphorus now has a positive charge. So if we attack the phosphorus, we can actually get a good leaving group. So anything with a positive charge, you can pretty much attack and just substitute the bonds there. And you have yourself a good leaving group now. Okay. So this is what happens here. All right, so now the alcohol is acidic and it's bonded to a phosphorus atom. That makes this now a very good leaving group, just like we saw before with dinyl chloride and PX3. Okay, so let me just make a little room here. All right, so this negative charge on the oxygen that we just formed is going to deprotonate this acidic hydrogen that we just drew out. Okay, so very similar to the step 2 we did, deprotonation of the alcohol. The ester, the phosphorus ester. Now we get R, O, all right. So when the leaving group has a charged part nearby, we can actually form an excellent leaving group now, and then the nucleophile can come in and attack. Okay. So here we get this here, and the byproduct that you can isolate is this group, and I'm pretty sure it's very water soluble, so you can actually isolate this by just washing the mixture. All right, so now this nitrogens, they have the capacity to do a lot of hydrogen bonding, so now you can easily wash this away from your product. Okay, so that's easily separated, so this is a byproduct. All right, so that's the end of the third step. The nucleophile attacks, you get this byproduct, and now you're ready. The alcohol attacks, and now you're ready to actually do the substitution. Okay, so the last step here, let's zoom out a bit. Number 4. Okay, number 4, your nucleophile approaches the modified alcohol okay, just like we saw before. Okay, this bond actually goes to form a double bond, so you can neutralize your leaving group here. So we get a SN2 product, like we saw before. Okay, so here's the SN2 product. All right, and then the byproduct here that is a solid, so this is called a phosphine oxide. So PPH3, and this is called phosphine oxide. So the downsides of this reaction is that the byproducts are kind of problematic to isolate or separate, but all in all, it does represent a good transformation here. And these reactions, Mitsunobu reaction, has been modified to be better nowadays. So, but this is the major thing we get. An SN2 project, and then the neat thing here, everything is added in one pot, one flask, and everything just happens like that. Okay, so that's the cool thing about it. So here I'll just note here just a few cool things about it. One operation does not matter which order you add the reagents, although that can play a role in how well the reaction goes. But we call it a one-pot reaction, where the order of addition of your reagents does not play a big role in the outcome of the reaction. So all 4 reagents are added at once. So this is also called a multi-component reaction. A few of these reactions that work like this were made at Davis. All right, so they like these type of reactions. All right, so I would say here this reaction is useful for forming esters with inversion. Okay, so for example, let's say we have our alcohol here, and it's an R group, and it has one stereocenter. Okay, well, I can convert this immediately with an ester, like so. So here's the prime example why this is pretty cool. So here's a benzoic acid. All right, we do our Mitsunobu reaction, PPH3. And then I'll just write this out one last time. All right, we get inversion of stereochemistry because it's an SN2 reaction. All right, the byproducts here, PH3, phosphine oxide. Oops, sorry, I forgot the phosphorus. My bad. Plus the byproduct of the dead reagent. All right. But I can actually just do sodium hydroxide here, and I will get out my alcohol again, but I've inverted the stereochemistry. So that's the best part of this reaction. You invert the chiral center. Okay, so if you need to invert your starting material right here, if you need to invert this chiral center, using the Mitsunobu reaction is one of the best ways to do that. Because if you try to do, first convert to alkyl halide and then try to use sodium hydroxide, if it's secondary, you might get elimination. So that's the only downside, okay? So this is the best way to do that. All right. So almost out of time here, but are any questions on that reaction? A long one, but just think it's a way to convert your alcohol, get the alcohol out of the get the enantiomer of the alcohol. So that's the best thing for the Mitsunobu. All right. So if you see, okay, my alcohol, I need the enantiomer. Oh, I'm just going to do Mitsunobu reaction, hydrolysis, and I get the target molecule. Okay. All right. So with the few minutes we have, let's just start talking about ethers. So we've kind of talked about naming ethers, but not a whole lot. So they're called alkoxy alkanes. So alkoxy alkanes. All right. So with naming, we just have to go from the start here. So let's start with the naming. All right. Acyclic ethers, okay, are named as alkoxy alkanes. All right. All right. So you have to find the longest chain that contains the ether, but the shorter chain is named the substituent. So what's the longest chain here? 5, right? So 1, 2, 3, 4, 5. We also have to number this chain because you have to know how long this is. So that's a 3. So this will be, so the oxygen comes at what number in the chain of the longer chain here? 2. So 2 propoxy, because that's an alkoxy, so propoxy pentane. And it's pentane because the longest chain is 5. Okay? So shortest chain, that's an alkoxy substituent. Then you find the longest chain, that's the parent name. All right. Sometimes you can have 2 oxygen groups in the same chain. So for example, let's use this example. All right. Okay. So we should probably number. So since there's 2 ethers here, let's number at the ending that has the substituent that comes first alphabetically. So if we number at this side, 1 is closer to the ethyl group. So we want to do it that way, okay? So here is ethyl. Here is just methyl. So we're going to get 1 edoxy. All right. 3 methoxy. And then what's the parent name? All right, I think you're right. 3 carbons in the middle between the ethers, so propane. All right. And then, let's see. Well, let's just do one more. This won't be really quick, okay? Sorry, guys. So, what if we have an alcohol in there? How does that change things? Well, what would the parent name be in this case if there's an alcohol? Is this still an alkane? How did we name alcohols? What did the ending change to? All, right. So let's still number it. So you're going to still number it where the lowest number is given to the carbon with the OH group. Like that, okay? So at the 6th position, what do we have? Yes, so methoxy. Good. All right, and where does the alcohol start at? 3. So we can write 3-hexanol because it's a 6-carbon alcohol. Or you can write 6-methoxy hexan -3-all. Okay? But personally, I like the first one better. If you like that one too, just keep doing that one. All right, that'll be for today. We'll pick up Thursday talking about cyclic ethers. All right.